Hi, my name is Simon Gladman, and I work for the Vector and Numerics group here at Apple. Today, I'll be talking about some exciting new functionality in our machine learning library, Basic Neural Network Subroutines, or BNNS. For the last few years, BNNS has provided a comprehensive API for machine learning inference and training on the CPU. Today, we're making BNNS faster, more energy efficient, and far, far easier to work with. In this video, I'll introduce you to our next great API for CPU-based machine learning, BNNS Graph. I'll start by introducing you to our new API and explain some of the ways it can optimize machine learning and AI models. Then I'll look at the important features that help BNNS Graph meet the demands of real-time use cases. And later on, I'll talk to the steps that you need to take for your app to adopt BNNS Graph. Finally, I'll walk through how to implement BNNS Graph in Swift and how it can work with SwiftUI and Swift Charts. So, make yourself a cup of tea, settle down on your favorite chair, and let's dive into BNNS Graph. Just before we get started, let me share how BNNS fits into Apple's overall stack of machine learning frameworks. BNNS is one of the libraries on our Accelerate framework, and it allows you to integrate your model into your app. It accelerates machine learning on the CPU, and it's used by Apple's machine learning framework, CoreML. Our new API for CPU-based machine learning, BNNS Graph, allows the BNNS library to consume an entire graph rather than the individual machine learning primitives. Training is the initial step for deploying your model onto Apple platforms. And once the model has been trained, it has to be prepared, that is, optimized and converted for deployment on device. And after preparing the model, it's ready to be integrated in your applications. In this video, I'll be focusing on the integrate part of the workflow. To understand BNNS Graph, I'd like to first look at the classic BNNS API. Up until today, BNNS presented a set of layer-focused APIs and supplied the individual performance primitives, the building blocks that you would use for machine learning. For each single operation, such as a convolution, you would typically have to configure lots of details. You'd use an n-dimensional array descriptor to specify the arguments and their properties to the layer. This means you would create a descriptor for the input, a descriptor for the output, a descriptor for the convolution kernel or weights matrix, and, as you might have guessed, BNNS expected the convolution bias as one more array descriptor. Then you'd use those array descriptors to create a parameter structure, and pass that parameter structure to the function that creates the layer itself. And finally, you'd apply the layer during inference. If you wanted to use BNNS to implement an existing model, you'd have to code each layer as a BNNS primitive, and write the code for all the intermediate tensors. In the past few years, we have been working on a new API, BNNS Graph. BNNS Graph takes an entire graph that consists of multiple layers and the data flow between those layers, and consumes it as a single object, a graph object. For you, this means you don't have to write the code for each individual layer. Furthermore, you and your users will benefit from faster performance and better energy efficiency. Let's run through a quick summary of the workflow to integrate BNNS Graph into your app. You'll start with a CoreML model package or an ML package file. For more details on how to create an ML package, watch the Deploy Machine Learning and AI Models on Device with CoreML video. Xcode automatically compiles a package to an ML Model C file, and then you write the code that builds the graph from the ML Model C file. And the last step is to create a context to wrap the graph. And it's that context that performs inference. Because BNNS Graph is aware of the entire model, it's able to perform a number of optimizations that were not possible before. And, even better, these optimizations come for free. Here's an example of a small section of a model. The first layer in this section performs an element-wise addition of tensors A and B and writes the results into C. The next layer performs a convolution, and after that, the model applies an activation function to the convolution result. And finally, the slice layer writes a subset of the elements into TensorD. BNNS graphs optimizations include mathematical transformations. In this example, the slice operation is the last layer. This means all the preceding operations act over the entire tensor rather than just the slice. The mathematical transformation optimization moves the slice to the beginning of the model so that BNNS only needs to compute the subset of elements in that slice. Optimizing with layer fusion involves combining some layers into a single operation. In this example, BNNS has fused the convolution and activation layers. And another optimization is copy elision, where a slice operation may naively copy the data in the slice to a new tensor. BNNS graph optimizes the slice so that it passes a window onto the original data. By ensuring tensors share memory where possible, BNNS graph can also optimize memory usage and eliminate unnecessary allocations. In this example, tensors A and C can share the same memory, and tensors B and D can also share the same memory. BNNS graph's weight repacking optimizations can repack weights from, for example, row major layout, to a blocked iteration order that can provide better cache locality. You don't need to write any code to benefit from these optimizations. They happen just like that. And they can provide performance that's, on average, at least 2 times faster than previous BNNS primitives. So, because our new API is ideally suited to real-time use cases, I'll be looking at such a use case, working with audio by adding BNNS graph to an audio unit. Audio units allow you to create or modify audio and MIDI data in an iOS or macOS app, and these include music production apps such as Logic Pro and GarageBand. An audio unit that uses machine learning can offer functionality such as separating audio to isolate or remove vocals, segmenting audio into different regions based on content, or applying timbre transfer to make one instrument sound like another. In this demonstration, I'll keep things simple and create an audio unit that bit crushes or quantizes audio to give a distorted effect. The main requirements for real-time processing are to avoid any memory allocations or multi-threading during the execute phase, as doing so may incur a context switch into kernel code and lead to defeat of the real-time deadlines. BNNS graph offers you fine-grained control over the compilation and the execution of models, and you're able to manage tasks such as memory allocation and whether execution is single or multi-threaded. I'm now going to show you how to create an audio unit project that adopts BNNS graph. Xcode makes creating an audio unit really easy because it includes a template that creates an audio unit extension app. I'll get started by dragging and dropping my BitCrusher ML package file into the project navigator. Xcode compiles the ML package into the ML Model C file that we'll use to instantiate the BNNS graph. So that's the first 2 steps done. Now that I have the ML Model C file available inside Xcode, I'm ready to create a BNNS graph object and wrap it in a modifiable context. You'll only build the graph once, so typically you'll do this in a background thread after your app starts up, or when your user first uses a feature that depends on machine learning. Graph compilation processes the compiled core ML model into an optimized BNNS graph object. This object contains a list of kernels that inference invokes and a memory layout map for the intermediate tensors. The Xcode template uses Swift and SwiftUI for the business logic and user interface, and C++ for real-time processing. The C++ DSP kernel header file is where all of the signal processing takes place in this project, and that's where I'll be adding the BNNS graph code. To do that, I will get the path for the ML Model C, build the BNNS graph, create the context, set the argument type, and create the workspace. Now, let's see how to write the code. Here's the code to get the path to the ML Model C file. Recall that I copied just the ML package file into the project, and Xcode has generated the ML Model C file from the package. To specify that the graph only uses a single thread during execution, I'll create a compilation option structure with the default settings. The default behavior is that BNNS graph executes on multiple threads. So I'll call the set target single thread function to change that. Now I'll use the compilation options and the path to the ML Model C file to compile the graph. The graph compiled from file function creates a graph. Note that I pass null as the second argument to specify that the operation compiles all the functions in the source model. And when the compilation completes, I can safely deallocate the compilation options. So that's step 3 done. We have created the graph. Now that we have the graph, which is immutable, the context make function wraps the graph in a context, which is mutable. BNNS graph requires a mutable context to support dynamic shapes and certain other execution options. The context also allows you to set callback functions so that you can manage output and workspace memory yourself. BNNS graph can work with tensor structures that specify shape, stride, and rank and point to the underlying data. Or it can work directly with pointers to the underlying data. Because this demonstration will work directly with audio buffers, I'll specify that the context arguments are pointers. We want to make sure BNNS doesn't allocate any memory while it's processing the audio data. So during this initialization, I'll create the page-aligned workspace. I need to update the context so that it knows the maximum size of the data it'll be working with. To do that, I'll pass a shape that's based on the maximum frames that the audio unit can render to the set dynamic shapes function. Now, the get workspace size function returns the amount of memory that I need to allocate for the workspace. The workspace memory must be page aligned, and I'll call aligned alloc to create the workspace. It's important to note that the argument order in my original Python code may not be the same as the argument order in the ML Model C file. The graph getArgumentPosition function returns the correct position for each argument that I'll pass to the execute function a little later. And now we have the properly configured context. Just before we move on, I'd like to briefly mention some other options. While we were working with the compilation options, we had the opportunity to set an optimization preference. By default, BNNS optimizes the graph for performance, which is perfect for the audio unit. Optimizing for performance means that additional work may be moved to the compile phase, even if it increases the footprint of the BNNS graph object. However, if the footprint of your app is important, you can also optimize for size. Optimizing for size means that data will be left in the smallest possible form, but this may decrease execute performance due to the cost of performing transformations. Another tip is that BNNS graph includes a function that enables NaN and infinity checks. This debugging setting will help you detect issues such as infinities and tensors when 16-bit accumulators overflow. However, you don't want to enable this check in your production code. And there we go. We've initialized the graph and context, specified single-threaded execution, and created the workspace to ensure BNNS doesn't perform any allocations. We are ready to execute the graph. Let's now take a look at the code required to do just that. The setBatchSize function sets the size of the first dimension of the input and output signal shapes to the number of audio samples in the frame. In this case, the second argument refers to the function name in the source file. However, because the source file only contains a single function, I can pass null. I'll pass the 5 arguments, the output and input signals, and the scalar values that define the amount of quantization as an array to the execute function. The first argument I'll add is the output signal. I'll specify the data pointer and the data pointer size fields based on the output buffer for the current audio channel. The next argument is the input signal. Much like the output, I'll specify the data pointer and the data pointer size fields, but based on the input buffer for the current audio channel. And the next arguments are the 3 scalar values that are derived from the sliders in the user interface. And now I can execute the function. The graph context execute function accepts the context, the arguments, and of course that important workspace. On return, the output pointer contains a result of the inference. As with the setBatchSize function, the second argument refers to the function name in the source file. And since the source file only contains a single function, I pass null. Finally, let's take a look at how to integrate BNNS graph in a Swift project. One perfect use case for using Swift is to implement our BNNS graph into the Swift UI component of our audio unit. This will allow the audio unit's user interface to display a sine wave that's been processed by the same model with the same parameters as the audio signal itself. The user interface component of the audio unit uses Swift UI and applies the bit crusher model to data that contains sample count elements and represents a smooth sine wave. The source chart data buffer stores the sine wave representation, and the destination chart data buffer stores the sine wave data after BNNS graph has applied the effect. These three buffers store the scalar values that the user controls with the sliders in the user interface. The API is consistent between C and Swift. So much like the audio processing code we looked at earlier, I'll define a graph and a context. And although Swift doesn't guarantee real-time safety, by providing a workspace, as we did in C++, BNNS graph won't need to do any memory allocations during execution. And this will help towards improving the performance and the energy efficiency of the audio unit. Next, I'll declare the argument index variables that define where the arguments live inside the arguments array. What you're seeing here is the code in the initializer method for the waveform display component, and this is where I create the graph, context, and workspace. The first step is to get the path to the MLModel.c file that Xcode has compiled from the ML package. Next, I'll compile the MLModel.c into a BNNS graph object. Then, just as I did in the C++ code, I create the graph context. You may be wondering why I don't use the same context for both the user interface and the audio processing. This is because the context can only execute on one thread at a time. Since the user may well be adjusting one of the sliders while the audio unit is processing data, we need separate contexts for each part of the project. I'll do a quick check to ensure that BNNS has successfully created the graph and context. And much like I did in the audio processing code, I'll work directly with pointers to the source and destination chart data. So I'll tell the context that the arguments are pointers rather than tensors. In this case, the batch size, the size of the first dimension of the source and destination signal data buffers, is the number of samples in the example sine wave. And after the set batch size function returns, the get workspace size function returns the correct size for the sample count. I'll calculate the indices into the arguments array, and whenever the user changes the slider value, Swift calls the update chart data function that applies the bit crusher effect to the sine wave. The first step in the update chart data function is to copy the scalar values into their corresponding storage. Then I'll use the indices to create the arguments array in the correct order. And now I can execute the bit crusher on the sample sine wave. On return of the execute function, Swift UI updates the chart in the user interface to show the bit crushed sine wave. I'll jump back into Xcode, where I've already added the Swift chart that displays the waveform. I'll declare the buffers that store the arguments, and I'll declare the graph, context, and argument indices. Inside the initializer, I'll initialize the graph and context, create the workspace and calculate the indices for the arguments. Then down in the update chart data function, I'll create the arguments function using the indices to ensure the correct ordering. And then execute the graph. Let's press the Xcode Run button to start the app and hear our bit crusher in action. Many thanks for your time. Allow me to wrap up with a summary. BNNS Graph provides the API that enables you to deliver high-performance, energy-efficient, real-time and latency-sensitive machine learning on the CPU. That's great for audio apps. Thanks again and best wishes.